You are listening to Data Architecture Reimagined, modern approaches for big data excellence. Like and subscribe to keep up to date on our latest audiobooks. Data Architecture Reimagined, modern approaches for big data excellence. Chapter 1, The Dawn of Modern Data Architecture. 1.1, The Ubiquity of Data. A new era. In the early 2000s, Kodak, a titan of photography, famously declared bankruptcy. While many factors contributed to its demise, a significant one was its inability to adapt to the digital revolution, despite inventing the first digital camera decades prior. Fast forward to today, and companies like Netflix, born in that same era as a DVD by mail service, have not only survived but thrived by perpetually reinventing themselves, powered by an insatiable appetite for data. Netflix's evolution into a global streaming giant, meticulously customizing content recommendations for each user, is a testament to the power of understanding and leveraging information. We live in an age where data isn't just plentiful, it's practically ubiquitous. From the smallest smart device in our pocket to the largest industrial machinery, almost everything generates a stream of information. Every online purchase, every swipe of a transit card, every scientific experiment, every video call, every sensor reading, all contribute to an ever-expanding universe of data. This exponential growth isn't just about volume, it's about the sheer variety, speed of generation, and the inherent complexity of managing it all. For businesses, this abundance of data presents a dual challenge and opportunity. On one hand, it's a goldmine of insights, a strategic asset that, when properly refined, can unlock unprecedented efficiencies, spark innovation, and create competitive advantage. Companies can predict market trends, personalize customer experiences, optimize supply chains, and identify new revenue streams. On the other hand, without a robust strategy and the right infrastructure, this data becomes an overwhelming deluge. It transforms from a valuable resource into a liability, a source of confusion, inefficiency, security risks, and missed opportunities. Many organizations find themselves drowning in data, unable to distinguish noise from signal, or worse, making crucial decisions based on unreliable or incomplete information. This is where data architecture steps in. It is no longer just a technical exercise. It's a strategic imperative that directly impacts an organization's agility, resilience, and ultimate success in the modern digital economy. 1.2, What is data architecture, and why does it matter now? At its core, data architecture is the blueprint for an organization's data assets. Think of it as the city plan for all the information an organization generates, collects, and relies upon. Just as a well-designed city plan ensures efficient traffic flow, proper zoning, and infrastructure that supports growth, a strong data architecture provides the structure, rules, and processes for clear, secure, and efficient data movement, storage, processing, and usage. This blueprint defines where data originates, from customer interactions to internal systems, how data is captured, the methods and technologies used for ingestion, where data is stored, the types of databases, data lakes, or warehouses, how data is transformed, the processes that clean, enrich, and prepare data for use, how data is accessed and consumed, the means by which applications and users derive insights, how data is governed, the policies and controls for security, privacy, and quality. Why does this matter so profoundly now? For decades, data architecture primarily focused on managing structured information in traditional relational databases, often on-premise. The focus was on ensuring transactional integrity and supporting standardized reporting. While effective for its time, this traditional approach falters dramatically in the face of today's big data challenges. Consider the consequences of a poor data architecture. Data silos. Information trapped in isolated systems, preventing a unified view of the business. Imagine different departments using conflicting customer lists. Inconsistency and unreliability. Data that is duplicated, has errors, or is not consistent across different systems, leading to conflicting reports and distrust in insights. Slow decision-making. The inability to quickly access and process necessary information, causing delays in identifying opportunities or responding to threats. Compliance risks. Failure to meet regulatory requirements around data privacy, like GDPR or CCPA, and security, leading to hefty fines and reputational damage. Stifled innovation, an inability to explore new data sources or leverage advanced analytics like machine learning, because the underlying data infrastructure is too rigid or complex. Conversely, a robust, modern data architecture delivers significant benefits: agility and scalability. The ability to rapidly adapt to new data sources, business requirements, and technological advancements, scaling effortlessly with data growth. Trustworthiness, reliable, high-quality data that stakeholders can trust, leading to better decision-making. Innovation, a flexible foundation to experiment with new analytical models, machine learning applications, and data-driven products. Competitive advantage, the capacity to derive insights faster and more effectively than competitors, translating directly into market leadership. Cost-effectiveness, optimizing storage and processing, especially in cloud environments, to reduce operational expenses. In essence, a well-conceived data architecture is the backbone of any data-driven organization, enabling it to transform raw information into a competitive asset. 1.3 Understanding Big Data. The 5 V's and beyond. The term big data became a pervasive buzzword, often misunderstood as simply lots of data. While sheer quantity is certainly a component, big data is more accurately defined by a combination of characteristics, often summarized by the V's: volume, velocity, variety, veracity, and value. Volume, this refers to the colossal amounts of data generated, measured in terabytes, petabytes, exabytes, or even zettabytes. Think of all the web traffic, social media posts, sensor readings from smart cities, financial transactions, and scientific simulations. A single autonomous vehicle can generate terabytes of data per hour from its cameras, LiDAR, and radar systems. This scale necessitated new storage and processing paradigms beyond traditional databases. Velocity. This speaks to the speed at which data is generated, collected, and processed, often in real time or near real time. Imagine millions of online trades happening in milliseconds, or fraud detection systems needing to flag suspicious activities instantly. For a large mobile gaming company, understanding player behavior and in-game economy trends requires processing hundreds of thousands of events per second to inform live adjustments or push immediate personalized offers. Dealing with this rapid flow is a core challenge. Variety, unlike the mostly structured, neatly organized data of the past, like rows and columns in a spreadsheet, modern data comes in a myriad of formats. Structured data, traditional relational database records, often found in CRM or ERP systems. Semi-structured data, data with some organizational properties but not a rigid schema, such as JSON files, common for web APIs, XML documents, or machine-generated log files. Unstructured data, data with no predefined internal structure, including text documents, emails, social media posts, images, audio recordings, and videos. To truly understand customer sentiment, a company might need to analyze service call recordings, unstructured audio, support chat logs, unstructured text, and product reviews, semi-structured text. Integrating insights from these diverse sources is crucial. Veracity, this addresses the trustworthiness and quality of the data. Is the data accurate, complete, consistent, and reliable? With data flowing from so many sources at such high speed, ensuring its integrity becomes a significant challenge. Faulty sensors, human error in data entry, or inconsistent data formats can all introduce noise that leads to flawed analysis and poor decisions. The insight you gain from data is only as good as the data itself. Value. Ultimately, the purpose of collecting, managing, and analyzing big data is to extract meaningful value. Without actionable insights, the other 4 V's are merely an expensive exercise. The challenge is to transform this raw, vast, fast, and varied information into something that drives business outcomes. Whether it's improved customer experience, optimized operations, or disruptive innovation. Beyond these core 5, other V's are sometimes mentioned, such as variability, changes in the meaning of data over time, or validity, ensuring data accuracy meets specific business rules. Regardless of the specific number of VS, the key takeaway is that big data is fundamentally different from traditional data, requiring a holistic, adaptable approach to its architecture. 1.4. The evolution of data management and the data architect's role. The role of managing an organization's data has evolved dramatically alongside the data itself. In earlier decades, the database administrator, DBA, was the primary custodian, focusing on the installation, maintenance, and performance tuning of relational databases. Their world was primarily one of structured data, ensuring transactions were reliable and reports could be generated from well-defined schemas. As data volumes grew and its variety diversified, particularly with the rise of the internet and web applications, the data engineer emerged. This role focused on building and maintaining the pipelines that move and transform data from various sources into centralized repositories like data warehouses. Data engineers became adept at programming, working with distributed systems, and handling batch processing. The advent of big data, cloud computing, and advanced analytics like machine learning introduced a new level of complexity and opportunity. This environment necessitated a more strategic, holistic role, the data architect. The data architect doesn't just manage databases or build pipelines, they design the entire ecosystem. The modern data architect's scope is expansive, encompassing strategic planning, aligning data strategy with overall business objectives. Infrastructure design, choosing and configuring the right cloud services, storage solutions, and processing engines. Data modeling, designing logical and physical data structures across various types of databases and data lakes. Pipeline design, overseeing the flow of data from ingestion to consumption, ensuring efficiency and reliability. Governance and security, implementing frameworks for data quality, privacy, regulatory compliance, and access control. Technology selection, evaluating and recommending tools and platforms, open source, commercial, cloud-managed, that fit the organization's needs. Collaboration and communication, bridging the gap between business stakeholders, data scientists, data engineers, and IT operations, translating business needs into technical specifications and vice versa. In essence, the data architect is the master planner, thinking several steps ahead to ensure that today's architectural decisions don't become tomorrow's limitations. They are responsible for creating a flexible, scalable, and secure data landscape that truly serves the organization's strategic goals. 1.5. What you'll learn in this book. This book is designed to provide you with a comprehensive understanding of modern data architecture, equipping you with the knowledge and principles necessary to navigate the complex world of big data. We will move beyond just naming technologies to exploring the underlying concepts and design patterns that make them effective. Our journey will begin by establishing core concepts and foundational principles. We'll then delve into the specifics of data acquisition, exploring how data makes its way into your systems. From there, we'll examine the diverse landscape of data storage solutions, from traditional warehouses to modern data lakes and lakehouses. We'll then dissect the processes of transforming raw data into valuable insights and how to orchestrate these complex workflows. Subsequent chapters will focus on how to make data accessible for consumption and integrate with critical functions like machine learning. A significant portion of our exploration will be dedicated to the indispensable topics of data governance, quality, security, and privacy, the guardians of any robust data architecture. We will then examine cutting-edge architectural paradigms like data mesh and data fabric, and understand how cloud-native approaches revolutionize data management. Finally, we'll equip you with a conceptual toolkit of essential technologies and guide you through best practices for building future-proof architectures, measuring success, and understanding the evolving role of the data architect itself. Whether you are an aspiring data professional, an experienced engineer, a technical leader, or simply someone eager to understand the strategic impact of data in today's world, this book will provide a clear, practical, and engaging guide to mastering modern data architecture. Let us begin this exciting exploration. Chapter 2, Core Concepts and Foundational Pillars. 2.1, The Traditional versus the Modern. a shifting paradigm. For decades, the world of data management operated on relatively stable ground. Data was primarily structured, housed in powerful, centralized relational databases, and processed in predictable batches. Think of a meticulously organized local library. Every book has a specific shelf, every piece of information fits a predefined category, and new additions must conform perfectly to the established system. This system, while robust for its time, mirrors traditional data architecture. Structured focus, primacy given to structured, tabular data fitting rigid schemas. On-premise infrastructure, data systems largely resided within an organization's own data centers, requiring significant upfront investment in hardware and maintenance. Batch processing, data processed in fixed cycles, e.g. nightly, weekly, suitable for historical reporting and predictable analytics. ETL dominance. Extract, transform, load ETL was the prevailing pattern, where data was heavily preprocessed and refined before being loaded into a data warehouse. This traditional approach offered strengths in data consistency, integrity, and performance for well-understood, predictable workloads. However, it proved fundamentally inflexible when confronted with the big data, revolution's sheer volume, rapid velocity, and diverse variety. It was like trying to manage the chaotic, dynamic growth of a bustling metropolis using only the rigid rules of a small, tranquil village. Modern data architecture, by contrast, is more akin to that sprawling metropolitan city, constantly adding new districts, integrating diverse transportation systems, and adapting to millions of new inhabitants and activities. It is distributed by design, leveraging interconnected systems and services, often across cloud environments. Flexible and adaptable, capable of ingesting and handling data in any format, structured, semi-structured, unstructured, and adapting to evolving business needs. Cloud native, primarily built on the elastic, scalable, and cost-effective infrastructure of cloud computing, leveraging managed services where possible. Real-time capable, embracing stream processing to derive immediate insights from data in motion. ELT preferred, increasingly favoring extract, load, transform, ELT, where raw data is loaded first and transformations occur within the analytical environment itself. This shift isn't just about technology, it's a fundamental change in philosophy. Modern data architectures prioritize agility, scalability, and the ability to extract value from all data, regardless of its original form or speed of arrival. 2.2 Key principles of modern data architecture. Regardless of the specific tools or technologies employed, robust modern data architectures are built upon several foundational principles. Scalability, the ability of a system to handle increasing amounts of data or workload without significant degradation in performance. In big data, this almost always implies horizontal scalability, meaning you can increase capacity by adding more machines or nodes to the system, rather than relying on a single, more powerful and expensive machine. Vertical scalability. You want your data architecture to grow seamlessly as your data and user base expand, ensuring that the system can perpetually adapt to demand. Reliability and resilience, ensuring that the data architecture consistently performs its intended functions under stated conditions for a specified period, and can gracefully recover from failures. This involves designing for high availability, minimizing downtime, disaster recovery, the ability to recover from major outages, and fault tolerance, the capacity to keep operating even if some components fail. Data pipelines, for instance, should be designed to be rerunnable and idempotent, meaning they produce the same result even if executed multiple times due to a process restart. Flexibility and agility, the capacity of the architecture to adapt quickly to changing business requirements, new data sources, evolving schemas, and emerging technologies. This often means favoring flexible data models that can accommodate new attributes without breaking existing systems, and adopting modular, loosely coupled components that can be updated or replaced independently. Agility is about shortening the time from data ingestion to actionable insight. Security and privacy, building protection into the architecture from the ground up rather than adding it as an afterthought. This encompasses authentication, verifying user identities. Authorization, granting appropriate access levels to data based on roles and permissions. Encryption, protecting data both when it's stored data at rest and when it's moving across networks, data in transit. Data masking/tokenization, obscuring sensitive data while maintaining its utility for analysis. Compliance with regulations like GDPR, CCPA, and HIPAA. A secure architecture safeguards sensitive information and builds trust. Cost-effectiveness, optimizing the use of resources to achieve business objectives without unnecessary expenditure. In cloud environments, this involves understanding pay-as-you-go models, choosing the right service tiers, optimizing storage costs, e.g., data compression, tiered storage, and ensuring compute resources scale down when not needed. Cost-effectiveness is not just about raw compute power, but the total cost of ownership, including operational overhead. Observability, the ability to understand the internal state of a system merely by looking at its external outputs, logs, metrics, traces, and events. For data architecture, this means having robust monitoring, alerting, and logging systems in place to track data flow, identify bottlenecks, detect anomalies, diagnose failures quickly, and ensure overall system health. If you can't see what's happening to your data, you can't manage it effectively. 2.3 The data lifecycle, a comprehensive view. Regardless of the industry or specific use case, data generally follows a consistent lifecycle within any organization. Understanding these stages is fundamental to designing an effective architecture. Ingestion acquisition. This is where data enters the system. It involves collecting raw data from various sources such as operational databases, application logs, IoT sensors, third-party APIs, clickstreams, social media, and more. This stage deals with the velocity and variety of data, often requiring specialized tools for real-time streaming or efficient batch loading. Storage. Once acquired, data needs a place to live. This stage focuses on choosing the appropriate storage solutions based on the data's type, volume, access patterns, and intended use. Modern architectures often employ a mix of storage technologies, including data lakes for raw, varied data, data warehouses for structured, analytical data, and specialized NoSQL databases for specific application needs. Processing transformation. Raw data is rarely in a form ready for direct analysis. This stage involves cleaning, validating, transforming, integrating, and enriching the data. It might include standardizing formats, correcting errors, joining disparate datasets, aggregating values, or applying machine learning models to derive new features. The goal is to refine raw data into a clean, consistent, and usable format for downstream applications. Serving consumption. This is the stage where the processed data is made available to business users, applications, and other systems to derive insights and enable actions. This can take many forms: dashboards and reports for business intelligence, data feeds for machine learning models, APIs for microservices, or direct queries by data analysts and scientists. The emphasis here is on discoverability, accessibility, and performance. Governance management. This is an overarching, continuous process that spans the entire lifecycle, ensuring that data is managed effectively and responsibly. It encompasses practices for data quality, data security, privacy, compliance with regulations, metadata management, data about data, master data management, MDM, and establishing clear roles and responsibilities for data ownership and stewardship. Governance ensures trust and unlocks the full value of data. These stages are not strictly sequential, but often overlap and loop. For example, data processed for one purpose might become raw input for another process. Effective data architecture ensures smooth transitions and robust controls across all these phases. 2.4 Demystifying data types: structured, semi-structured, unstructured. Modern data architectures must be capable of handling the entire spectrum of data types, a significant departure from the relational database-centric world of the past. Structured data: this is data that strictly adheres to a predefined schema and is highly organized. Imagine a spreadsheet or a traditional relational database table with clearly defined rows and columns. Each piece of information fits neatly into a specific field, and its type, text, number, date is known upfront. Examples include customer addresses, financial transactions, product IDs, and sensor readings from a climate control system. Structured data is highly amenable to traditional analytical tools and SQL queries. Semi-structured data. This type of data has some organizational properties, allowing for grouping and hierarchy, but does not conform to the rigid, tabular structure of relational databases. It often contains tags or markers to separate semantic elements and enforce hierarchies. Think of it as a self-describing format. Common examples include JSON, JavaScript Object Notation, widely used in web applications and APIs, representing data in key-value pairs and arrays. XML, Extensible Markup Language, historically used for document markup and data exchange. Log files, often generated by applications or servers, containing structured timestamps, error codes, and less structured diagnostic messages, components within the same entry. Semi-structured data offers more flexibility than structured data for evolving systems and is often a good fit for NoSQL databases that support flexible schemas. Unstructured data. This is data that has no predefined internal structure or organization. It does not fit into a conventional row-column database model and often requires advanced techniques like natural language processing or computer vision to derive meaning. Examples include text, documents, Word, PDF, emails, social media posts, chat transcripts, customer reviews, news articles. Media, images, audio files, voice recordings, podcasts, video files, surveillance footage, streamed content. Other, satellite imagery, scientific experimental data, medical scans. While unstructured data is challenging to process and analyze, it often holds immense value. Think of analyzing customer sentiment from product reviews or detecting anomalies from surveillance videos. Modern data architectures must provide frameworks to store, manage, and process this vast and often murky pool of information. The challenge and opportunity for data architects is to build systems that can efficiently ingest, store, process, and analyze all three types of data, often simultaneously, to provide a comprehensive view of business operations. For instance, understanding customer behavior might involve combining structured transaction data with semi-structured website clickstream logs and unstructured customer service call transcripts. 2.5 Architecture as a business enabler. Ultimately, the purpose of data architecture is not merely technical elegance. It is to enable and accelerate business outcomes. A common pitfall for technical teams is to build sophisticated systems that, while technically sound, fail to address the core business needs or provide actionable insights. The data architect stands as a crucial bridge between the world of business strategy and technical implementation. Their role involves translating business requirements, taking vague business goals, such as improve customer satisfaction or optimize supply chain efficiency, and breaking them down into concrete data requirements, identifying necessary data sources, transformations, and consumption patterns. This requires strong communication skills and a deep understanding of the business domain. Understanding key performance indicators, KPIs, knowing which metrics drive the business, and designing the data flows that reliably generate these KPIs. If a business needs to track customer churn, the architecture must ensure all relevant customer interaction and demographic data is collected, cleaned, and joined to enable accurate churn prediction models, aligning with strategic objectives, ensuring that data investments support the organization's overarching vision and strategic priorities. For example, if a company's strategy is focused on personalized customer experiences, the data architecture must be capable of quickly integrating and analyzing individual customer behavior across multiple touchpoints. Consider a large retail company that seeks to deeply understand its customers to personalize marketing campaigns and optimize product recommendations. This seemingly simple business goal requires a sophisticated data architecture that can ingest structured data from point-of-sale systems, transaction history, product IDs, purchase dates. Combine it with semi-structured data from website clickstreams, pages visited, items viewed, time spent, email marketing interactions, and mobile app usage. Integrate unstructured data from customer service, chat logs, identifying common complaints, sentiment, and social media comments about the brand. Process all this data to build a comprehensive customer 360-degree view, identifying purchasing patterns, preferences, and potential churn risks. Serve these insights to marketing teams for targeted campaigns, to product teams for insights into popular products, and to customer service for personalized support. Without a well-designed, modern data architecture, this complex mosaic of information would remain fragmented, making true customer understanding impossible. The architecture is not just a tool. It's the strategic engine that drives business intelligence, innovation, and ultimately, competitive advantage in the data-driven era. Chapter 3. Ingesting the Deluge. Data Acquisition Strategies. 3.1 Where does data come from? Diverse sources. Before data can be transformed into insight, it first needs to be captured. This initial stage, often called data ingestion or acquisition, is the critical on-ramp to any data architecture. In the era of big data, the sources are incredibly diverse, reflecting the digital footprint of nearly every human activity and machine operation. Understanding these origins is key to designing effective ingestion strategies. Common data sources include transactional databases, OLTP systems. These are the operational heartbeats of a business. They power customer relationship management, CRM systems, enterprise resource planning, ERP systems, inventory management, e-commerce platforms, and financial applications. Data here is typically highly structured, critical, and constantly changing, updates, inserts, deletes. Capturing changes from these systems efficiently without impacting their performance is a key challenge. Application logs and system telemetry. Every software application, server, and network device generates logs detailing events, errors, user activities, and performance metrics. These logs are often semi-structured, e.g., in JSON or text formats, and can accumulate at very high volumes and velocity, providing crucial operational intelligence for monitoring, troubleshooting, and security analysis. APIs, application programming interfaces. Data from third-party services, social media platforms, whether agencies, financial markets, or partners, often comes via APIs. These provide controlled, programmatic access to data, typically in JSON or XML format. Ingesting from APIs involves making specific requests and handling responses, often within rate limits. IoT devices and sensor networks. The Internet of Things is a massive generator of data, from smart home devices and connected cars to industrial sensors monitoring vibrations, temperature, pressure, or location. This data is often high volume, high velocity, and can be structured, e.g., a temperature reading, or less structured, e.g., complex signals. Website clickstreams and mobile app events. Every user interaction on a website or mobile application, a page view, a click, a search, a purchase, an add to cart action, generates an event. This data is critical for understanding user behavior, optimizing user experience, and personalizing content. It often comes in high-volume streams, requiring fast, scalable ingestion. External datasets. These can be publicly available datasets, e.g., government statistics, commercial data providers, e.g., market research firms, or open-source data repositories. They often arrive as bulk files, CSV, Parquet, JSON, but can also be accessed via APIs or data-sharing platforms. Document and media files. Unstructured content like customer support emails, contracts, product images, marketing videos, audio recordings of calls, or scientific papers. These often reside in file storage systems and require specialized handling for text extraction, image analysis, or transcription before they become usable. The diversity of these sources means that a one-size-fits-all ingestion strategy is rarely sufficient. A robust data architecture needs a versatile toolkit to handle each type of data effectively. 3.2 Batch versus stream processing, choosing the right tempo. A fundamental decision in data ingestion is choosing between batch processing and stream processing. This choice is primarily dictated by the urgency of insights needed and the characteristics of the data flow. Batch processing, concept. Data is collected over a period, e.g., an hour, a day, a week, and then processed in large chunks. It's like gathering all the mail from your mailbox once a day and then sorting and opening it all at once. Characteristics, periodic, runs at scheduled intervals. High latency, insights are available after the batch processing is complete, which could be minutes to hours later. Efficient for large volumes. Optimized for processing large historical datasets efficiently without continuous resource consumption. Simpler error handling, easier to reprocess an entire batch if an error occurs. Use cases: end-of-day financial reporting, monthly sales analysis, quarterly business intelligence dashboards, historical data analysis for machine learning model training, bulk data migrations, consolidating daily logs. When to use: when freshness of data latency is not critical and you have large volumes of data that can be efficiently processed in groups. Stream processing, concept. Data is processed continuously as it arrives in motion. It's like reading each piece of mail as it arrives, one by one, immediately. Characteristics, continuous, always running, reacting to events as they occur. Low latency, aims for near real-time insights, often within milliseconds or seconds. Event-driven, optimized for individual events or small windows of events. Complex error handling, requires careful design for reliability, e.g., handling out-of-order events, ensuring exactly once processing. Use cases: fraud detection in financial transactions, real-time personalized recommendations on e-commerce sites, monitoring IoT sensor data for immediate alerts, e.g., abnormal machinery temperature, live website analytics, real-time bidding in advertising, tracking package movements in a global logistics company. The logistics company tracks millions of packages, and knowing a package's precise location and status at any given moment is critical for customer service and operational efficiency. This requires continuous stream processing of location updates, rather than waiting for an overnight batch to process. When to use: when immediate action or insight is required and data flows continuously. It's important to note that many modern data architectures employ a hybrid approach, often referred to as a kappa or lambda architecture, which we'll discuss in Chapter 10. This involves combining batch and stream processing to leverage the strengths of both, serving different analytical needs from the same underlying data. For instance, a retail company might use stream processing for real-time inventory updates on its website, but rely on daily batch processing for comprehensive sales trend analysis. 3.3. Data ingestion patterns and methodologies. Once you've decided on the tempo, batch or stream, you need an actual mechanism for moving the data. Several core patterns and methodologies dominate modern data ingestion. Extract, transform, load, ETL. This is the traditional workhorse of data warehousing. Extract, data is pulled from the source system. Transform, data is cleaned, converted, validated, aggregated, and otherwise manipulated to fit the target data model before it is loaded. This is done on a dedicated ETL server or processing engine. Load. The transformed data is then loaded into the target data warehouse. Pros: data arrives at the destination in a clean, standardized format, good for tightly controlled, predefined schemas. Cons: can be slow and resource-intensive for large volumes. Transformations can be complex to manage, less flexible for evolving data needs. Extract, load, transform, ELT. This pattern has gained significant popularity with the rise of cloud computing and powerful, scalable data warehouses and data lakes. Extract, data is pulled from the source. Load. The raw, extracted data is loaded directly into a target data lake or cloud data warehouse. This leverages the storage and compute scalability of these platforms. Transform. Once loaded, the transformations are performed within the target system, leveraging its native processing capabilities, e.g., SQL queries in a cloud data warehouse or Spark jobs on a data lake. Pros: faster initial loading of data, maintains raw data for future, unforeseen, analytical needs, leverages the immense processing power of modern data platforms, more flexible as transformations can be changed without re-extracting raw data. Cons: requires the target system to have robust transformation capabilities, can lead to data swamps if raw data is loaded without proper governance. Change data capture, CDC. This methodology focuses on capturing only the changes, inserts, updates, deletes that occur in a source database in near real time, rather than extracting the entire dataset periodically. How it works conceptually. CDC tools typically read the transaction logs, redo logs, write-ahead logs of a database, providing a continuous stream of changes without impacting the source system's performance. Pros. Very efficient for moving only delta changes, provides near real-time synchronization, reduces load on source systems. Use cases. Replicating operational databases to analytical data stores, populating caches, real-time data warehousing. API-driven ingestion. This involves making direct calls to REST-TFL or GraphQL APIs exposed by source systems or third-party services. How it works. A Python script, a data integration tool, or a custom application pulls data via API requests. Pros. Controlled access, often well-documented data formats, allows for targeted data retrieval. Cons. Rate limits, API versioning changes, requires careful error handling for network issues or API failures. Event-driven ingestion. This is a key pattern for stream processing, where data is ingested as a continuous stream of discrete events, e.g., a credit card transaction, a sensor reading, a user click. How it works. Events are published to a central message queue or event streaming platform and then consumed by various subscribers. Pros. Highly scalable, decoupled architecture. Publishers and consumers don't need direct knowledge of each other, resilient to failures. 3.4 Key technologies and conceptual tools for ingestion. While specific vendor tools change, the conceptual categories of tools remain consistent. Message queues, event streaming platforms. These are foundational for high-volume, real-time data ingestion. They act as durable, fault-tolerant buffers between data producers and consumers. Conceptual role. They ensure messages are delivered reliably, in order, within a partition, and can handle bursts of traffic without overwhelming downstream systems. They enable multiple consumers to read the same stream of data independently. Examples: Apache Kafka, an open-source distributed streaming platform, Amazon Kinesis, Azure Event Hubs. These typically manage a series of topics or streams to categorize events. Data integration platforms. These tools provide capabilities for orchestrating data movement and often include pre-built connectors to various data sources, graphical interfaces for defining data flows, and scheduling functionalities. Conceptual role. To simplify and automate the process of connecting to diverse sources, extracting data, and loading it into targets. They abstract away much of the underlying complexity of data connectors. Examples: tools like Informatica, Talent, Fivetran, Stitch, or cloud-native services like AWS Glue, Azure Data Factory, Google Cloud Dataflow. File ingestion tools. For bulk loading of files, from traditional SFTP servers to cloud object storage. Conceptual role. To efficiently transfer large files, e.g., CSV, Parquet, JSON dumps, from source systems into a data lake or cloud storage for further processing. Examples: simple scripting, cloud transfer services like AWS DataSync, Azure DataBox, or managed file transfer solutions. Data connectors SDKs. These are software components that allow applications or integration platforms to communicate with different data sources, e.g., JDBC ODBC drivers for relational databases, specific SDKs for cloud services, or APIs. When architecting ingestion, it's vital to focus on the conceptual role of these technologies. For instance, whether you choose Apache Kafka, Kinesis, or Event Hubs, their fundamental purpose of enabling scalable, fault-tolerant event streaming remains the same. The choice often comes down to ecosystem preference, existing expertise, and specific cost-feature trade-offs. 3.5 Challenges in ingestion. Scale, reliability, and data integrity. Building a robust data ingestion layer is a non-trivial task, fraught with challenges. Handling varying data formats and schema evolution. Data sources are rarely static. Schemas change, new fields are added, existing fields are deprecated. The ingestion pipeline must be resilient to these changes, either by being schema-agnostic, like loading raw data into a data lake, or by having mechanisms to detect and adapt to schema changes, ensuring data delivery guarantees. For critical data, it's essential to understand and design for delivery semantics. At most once. A message might be lost but never delivered more than once, e.g., for very high volume, less critical telemetry. At least once. Messages are guaranteed to be delivered but might be duplicated, requires downstream deduplication. Exactly once. Messages are delivered precisely once, even in the face of failures, the gold standard, but most complex to achieve, often involving idempotency in processing, managing backpressure and throughput. What happens when data producers generate data faster than consumers can process it? The ingestion layer must provide mechanisms, like message queues, to buffer data, preventing producers from being blocked or data being dropped, while allowing consumers to catch up at their own pace. Implementing robust monitoring and alerting. Failures in the ingestion layer can have catastrophic downstream effects. Critical ingestion pipelines require comprehensive monitoring to detect data loss, latency spikes, format deviations, or connectivity issues immediately, triggering automated alerts to the operations team. Data quality beyond format. Ingestion is not just about moving bytes, it's about moving meaningful data. Checks for basic data quality, e.g., null values, data type consistency, can and should begin at the ingestion stage to prevent bad data from polluting downstream systems. In summary, the ingestion layer is the unsung hero of modern data architecture. It's the critical first mile of the data journey, and its careful design ensures a reliable, scalable, and trustworthy foundation for all subsequent analytical and operational processes. Chapter 4, Storing the Big Picture, Data Lakes, Warehouses, and Beyond. 4.1, The Traditional Data Warehouse, Strengths and Limitations. For decades, the data warehouse served as the cornerstone of business intelligence and analytics for many organizations. Introduced in the 1980s, its purpose was clear: to aggregate and store historical business data from various operational systems in a structured format, specifically for analysis and reporting, separate from the transactional systems that ran daily operations. Imagine an impeccably organized, well-indexed library. Each book data record is cataloged perfectly, placed on its designated shelf, and ready to be quickly retrieved for a specific purpose. This analogy captures the essence of a traditional data warehouse. Purpose: primarily for structured, historical data analysis, business intelligence, and reporting. It helps answer questions like, how many products did we sell last quarter? Or, what was our revenue by region last year? Characteristics: predefined schema on right. Data must conform to a strict, predesigned model, often a star or snowflake schema, before it is loaded. If it doesn't fit, it's either cleaned and transformed via ETL processes, as discussed in Chapter 3, or rejected. Optimized for complex SQL queries. Designed for analytical queries that often involve joining large tables, aggregations, and complex calculations. Data integrity and consistency. Strong emphasis on maintaining accuracy and reliability, crucial for financial reporting and compliance. Strengths: high performance for structured queries. When well-designed, data warehouses are exceptionally fast for answering predefined analytical questions on structured data. Mature tooling and ecosystem. A wide array of established by tools, reporting solutions, and data modeling methodologies exist. Trustworthy data. Due to rigorous ETL processes and data validation, data within a warehouse is generally considered reliable for decision-making. Limitations: rigidity. Changing the schema or integrating new, unanticipated data sources can be difficult, time-consuming, and expensive. It's like having to rebuild parts of the library every time you introduce a new genre of books or a fundamentally different cataloging system. High cost and scalability challenges. Traditional data warehouses often required specialized hardware and software, making them expensive to scale, especially for massive data volumes. Poor fit for diverse data. They struggle with semi-structured and unstructured data, which needs extensive pre-processing to fit the relational model. This limits their utility for modern data science applications. Latency, primarily designed for batch processing, making real-time analysis difficult. While essential for much of the business reporting we rely on, the traditional data warehouse often became a bottleneck in the age of diverse, high-volume, and high-velocity data. 4.2 Embracing the data lake, flexibility and challenges. As businesses clamored for analytical insights from all their data, including web logs, social media feeds, IoT sensor data, and video, the concept of the data lake emerged. This new paradigm offered a seemingly limitless solution for storing raw, untransformed data at any scale or format. If the data warehouse is a meticulously organized library, the data lake is more like a vast, raw storage depot or a scientific laboratory's archives. It's where you dump everything without rigid organization because you might need it later for unforeseen experiments or analysis. Purpose: to store raw, unprocessed operational data in its native format, regardless of structure. It allows for future analysis where the exact questions are not yet known. Characteristics: schema on read. No predefined schema is enforced upon ingestion. The schema is determined when the data is read and processed for a specific inquiry. This offers immense flexibility. Built on cheap object storage, typically implemented using highly scalable and cost-effective object storage services, like Amazon S3, Azure Blob Storage, Google Cloud Storage, which are designed for durability and massive scale. Supports diverse analytical tools, can be accessed by a wide array of tools, e.g., big data processing frameworks, machine learning libraries, data science notebooks. Strengths: high flexibility. Can store any type of data, structured, semi-structured, or unstructured, in its raw form, preserving all original detail. Cost-effective scalability. Extremely economical for storing petabytes or even exabytes of data. Ideal for machine learning and data science. Data scientists often prefer raw, granular data for experimentation, feature engineering, and training complex models. Supports advanced analytics. Enables new types of analytics that are impossible or too difficult with traditional warehousing, e.g., sentiment analysis from social media, predictive maintenance from IoT data. Challenges: risk of data swamp. Without proper governance, metadata management, and documentation, a data lake can quickly turn into a data swamp. A chaotic, unmanaged repository where data is hard to find, understand, or trust. It becomes a dumping ground rather than a valuable asset. Data quality issues. Since raw data is ingested, inherent quality issues, inaccuracies, inconsistencies, duplicates are carried over, requiring rigorous data validation further downstream. Difficulty for business users. Business analysts who rely on SQL for querying might find it challenging to work directly with raw, unmodeled data in a lake. Performance for complex queries. While flexible, querying and joining vast amounts of raw data across different formats can be slow and computationally expensive without specialized processing engines. The data lake offered incredible flexibility, but introduced new challenges around data quality, governance, and usability for traditional business intelligence. 4.3 The rise of the data lakehouse. Unifying the best. Recognizing the strengths and limitations of both data warehouses and data lakes, a new architectural pattern emerged: the data lakehouse. The lakehouse architecture aims to combine the flexibility, low cost, and scalability of a data lake with the data management, performance, and reliability features traditionally associated with data warehouses. Think of the lakehouse as a hybrid structure, perhaps a modern, expansive superstore. It has a vast, raw materials section, like a data lake, but it also has highly organized aisles, like a data warehouse for curated products, all managed under one comprehensive inventory system. The core idea is to bring data warehousing capabilities directly to the data lake, eliminating the need for separate, often redundant, systems. This is primarily achieved through open table formats. These are critical enablers. Technologies like Delta Lake, Apache Iceberg, and Apache Hudi allow data stored in standard object storage, like Parquet or ORC files, to gain benefits typically found in databases, such as ACID transactions. ensuring atomicity, consistency, isolation, and durability for data operations, which is crucial for data integrity. This means multiple users can read and write data concurrently without conflicts, and operations either complete entirely or not at all. Schema enforcement and evolution. The ability to define and evolve schemas over time while maintaining compatibility. Time travel. Accessing historical versions of data, enabling reproducible analyses and easy rollback from errors. Performance optimizations. Indexing, caching, and data skipping techniques for faster query performance. Unified data plane. A single copy of data in the data lake can serve multiple workloads: buy and reporting, data science, machine learning, and stream processing, without needing to move or duplicate data into separate specialized systems. Benefits of the lakehouse. Single source of truth, reduces data duplication and eliminates inconsistencies between lakes and warehouses. Scalability and cost-effectiveness. Leverages the cheap storage and horizontal scalability of data lakes. Flexibility for all data types, handles structured, semi-structured, and unstructured data natively. Improved data quality and reliability. ACID transactions and schema enforcement bring data warehouse-like reliability to the lake. Simpler data management. Less complex architecture, fewer systems to manage and integrate. Supports diverse workloads. Facilitates BI, SQL analytics, data science, and machine learning on the same data. A large e-commerce company, for example, might use a lakehouse architecture. Their raw clickstream data, semi-structured, lands directly in the lakehouse. Transactional data from their traditional database, structured, is also streamed into the lakehouse. Using the lakehouse's capabilities, data engineers can then perform ELT transformations directly on this raw data within the lake itself, creating refined, curated tables for both daily BI dashboards and for data scientists to build recommendation engines. This avoids moving data to a separate data warehouse system, saving cost and improving data freshness. 4.4 Other modern storage solutions. While the data warehouse, data lake, and lakehouse represent broad architectural patterns, a wide array of specialized databases known as NoSQL databases have emerged to address specific data models, performance requirements, and scalability challenges that traditional relational databases and data warehouses were not designed for. The term NoSQL broadly means not only SQL, indicating they may or may not use SQL-like query languages. NoSQL databases, document databases, store data in flexible, semi-structured documents, typically in JSON or BSON format. Each document can have a different structure, making them good for rapidly evolving applications or content management. Conceptual fit, where data doesn't fit neatly into rows and columns, like user profiles with varied attributes, product catalogs, or content management systems. Key value stores, the simplest type of NoSQL database, storing data as a collection of key value pairs. They offer extremely fast read and write operations for simple data lookups. Conceptual fit, caching frequently accessed data, storing session information, or managing configuration data. Column family databases, designed to handle very large amounts of data distributed across many servers. They store data in columns that are grouped into column families, allowing for efficient retrieval of specific columns across many rows, especially good for analytics on wide tables. Conceptual fit, for time series data, large-scale event logging, or high-volume write applications where you need to store vast amounts of data that may be sparse. Graph databases, optimized for storing and querying highly interconnected data, where the relationships between entities are as important as the entities themselves. Data is stored as nodes, entities, and edges, relationships. Conceptual fit, social networks, recommendation engines, fraud detection, identifying suspicious connections, or supply chain analysis where relationships are complex. Object storage, while not a database in itself, distributed object storage services, e.g., Amazon S3, Azure Blob Storage, Google Cloud Storage, are absolutely fundamental to modern data architectures. They are the backbone on which data lakes and lakehouses are built. Conceptual role, provides massive scalability, high durability, and low cost for storing unstructured and semi-structured data, files, images, videos, logs, data lake content. Data is stored as objects in buckets, accessed via URLs. They do not enforce strict schemas or support complex transactional operations directly, but are the ideal landing zone for raw data. 4.5. Choosing the right storage for your data and use case. Given the diverse array of storage options, deciding where and how to store data becomes a critical architectural decision. There's no single best solution. The optimal choice depends on several factors: data type and structure. Is the data structured, semi-structured, or unstructured? Relational databases excel with structured data, NoSQL databases handle various semi-structured patterns, and object storage is ideal for raw, unstructured files. Access patterns. How will the data be read and written? Is it primarily for analytical queries, data warehouse/lakehouse, fast key-value lookups, key-value store, complex graph traversals, graph database, or continuous writes column family? Required scale. How much data will you store, and how fast will it grow? Object storage with a data lake or a cloud data warehouse handles petabytes, while a specialized NoSQL database may be better for a specific, high-velocity operational dataset. Performance requirements. What are the latency requirements for reads and writes? Real-time operational systems demand millisecond responses, while historical analytics might tolerate seconds or minutes. Cost constraints. Different storage solutions have different cost models: storage cost, compute cost, network transfer fees. Schema volatility. How often will the data model chain? Document databases offer high flexibility, while traditional data warehouses are more rigid. Tooling ecosystem and expertise. What existing tools do you use, and what is your team's familiarity with various technologies? The reality of modern data architecture is often polyglot persistence, the strategic use of multiple specialized data stores within a single system. A financial institution, for instance, might keep core banking transactional data in a highly structured relational database for integrity. Stream all transaction events into a data lakehouse for comprehensive historical analysis and machine learning model training. Use a graph database to detect complex fraud patterns across customer accounts and transactions in near real time. Store customer support call recordings, unstructured, in object storage for later transcription and sentiment analysis. Use a key-value store for quickly serving user preferences for their mobile banking application. Each storage technology is chosen for its unique strengths, contributing to a holistic data architecture that effectively supports the diverse and evolving needs of the organization. The data architect's skill lies in orchestrating these disparate elements into a cohesive and efficient whole. Chapter 5. Transforming Raw into Insight, Processing and Orchestration. 5.1 From Raw to Refined. The purpose of data transformation. Data, as it's ingested from its various sources, as discussed in Chapter 3, is rarely in a pristine state. It's often raw, messy, inconsistent, duplicated, or incomplete. Imagine trying to bake a cake directly with raw, uncracked eggs, flour still in the grain, and sugar from the beet. It just won't work. Data transformation is the essential culinary process that cleans, prepares, and shapes raw ingredients, data, into usable forms, making them palatable and digestible for analysis, reporting, and machine learning. The key purposes of data transformation include cleaning, removing errors, inconsistencies, or duplicate records. This might involve correcting typos in customer addresses, standardizing date formats, or handling missing values, e.g., by imputation or removal. Integrating, combining data from multiple disparate sources into a single, cohesive dataset. This often involves joining tables based on common keys, like customer ID, or merging different data formats. Aggregating, summarizing data to a higher level of granularity. For example, summing daily sales figures to calculate monthly totals or counting unique website visitors. Enriching, adding new, valuable information to existing data. This could involve geocoding addresses, appending demographic data, or inferring sentiment from text fields. Standardizing, converting data into a consistent format or unit. For example, converting all currencies to USD or ensuring all product categories use the same terminology. Structuring modeling. Adapting data to fit a specific schema or data model required by the target analytical system, e.g., a star schema in a data warehouse or features for a machine learning model. In data lakes and lakehouses, a common approach to managing data refinement is through conceptual layering, often referred to as medallion architecture or data zones. Bronze layer raw contains data in its original, untransformed state exactly as it was ingested. This layer is immutable and serves as the single source of truth for all raw data. Silver layer, cleaned conformed. Data in this layer has undergone initial cleaning, deduplication, and basic transformations. It's typically structured and conformed to consistent schemas, making it easier to query. This is where data from disparate sources might be joined. Gold layer, curated aggregated. This layer contains highly refined, aggregated, and business-ready data, specifically modeled for downstream consumption by dashboards, machine learning applications, or specific departmental reports. It's often optimized for performance. This layering provides a clear path of data evolution, allowing users to choose the level of refinement suitable for their needs while ensuring traceability back to the raw source. 5.2 ETL versus ELT revisited. Modern workflows. As discussed in Chapter 3, the terms ETL and ELT describe the sequence of data transformation. While both serve the purpose of refining data, their application and implications differ significantly in modern architectures. ETL, extract, transform, load, workflow. Data is extracted from source systems, transformed on a separate staging server or dedicated ETL engine, and then loaded into the target data warehouse. Characteristics. Transformations are often complex and predefined, requiring dedicated compute resources separate from the final store. Data loaded into the warehouse is already clean and conformant. Best for environments with a need for strict schema enforcement, extensive data cleansing before loading, or situations where the target database has limited processing power for transformations. It's still often used for specific data quality processes or when sensitive data needs to be masked before it even touches the main analytical store. ELT, extract, load, transform, workflow. Raw data is extracted from sources, immediately loaded into a scalable data lake or cloud data warehouse, and then transformed using the powerful compute capabilities of the target platform itself. Characteristics. Leverages cloud scalability. Transformations become SQL queries or data processing jobs run directly within the lake warehouse. The raw data remains accessible for diverse future uses. Best for modern cloud data architectures, big data environments, where raw data needs to be preserved, and where the target system offers scale-out compute for efficient transformation. This approach often leads to faster data ingestion and greater agility, as transformations can be iterated and rerun as needed without re-extracting large volumes of raw data. The choice of performing transformations in Spark on a data lake or via SQL in a cloud data warehouse depends on the data's structure and the analytical engine preferred. In today's cloud-native landscape, ELT often reigns supreme due to its flexibility and the ability to leverage the immense power of cloud data platforms for computation. This means transformation logic increasingly resides directly within the data platform, often managed as code. 5.3 Designing robust data pipelines. Data pipelines are the conveyor belts that move data through the transformation stages, from raw input to refined output. Designing them requires careful consideration to ensure reliability, performance, and maintainability. Core components of a pipeline: source connectors, tools or code to connect to and extract data from various systems. Processing engine, the compute layer that executes transformations, e.g., a cluster running Apache Spark, a cloud data warehouse processing SQL, or serverless functions. Transformation logic, the actual rules and code that define how data is cleaned, combined, and reshaped. Destination loader, mechanisms to load the transformed data into the proper data store, e.g., a data lake layer, a data warehouse table, or an application database. Monitoring and logging, essential systems to track pipeline health, performance, and identify errors. Scheduling and orchestration, tools to manage when and how pipeline steps run. Key design patterns for robust pipelines. Idempotency, a critical concept. An operation is idempotent if applying it multiple times produces the same result as applying it once. In data pipelines, this means if a processing step fails and is retried, it won't create duplicate records or incorrect aggregations. For example, an upsert operation, update if exists, insert if not, is idempotent. Fault tolerance, building pipelines that can recover gracefully from errors. This involves implementing retry logic for transient failures, having dead letter queues for unprocessable messages, and ensuring that component failures don't bring down the entire pipeline. Rerunability, backfilling, the ability to easily reprocess data for a specific time range or from a specific point in history. This is vital for correcting errors, applying new transformation logic to historical data, or recovering from outages. Schema evolution management. Pipelines must be able to handle changes in the structure of source data, e.g., new columns, renamed columns, changed data types, without breaking. This often requires flexible parsing capabilities or defined processes for updating transformation logic. Version control, treating data transformation logic, e.g., SQL scripts, Python code for Spark jobs, as software code and managing it in version control systems, like Git. This ensures traceability, collaboration, and the ability to roll back to previous versions. 5.4 Data processing engines, the computational powerhouse. At the heart of the transformation process lies the data processing engine, which provides the computational power to execute complex operations on large datasets. Distributed processing concepts, e.g., Apache Spark, for big data batch processing and increasingly for streaming, distributed computing frameworks are essential. Conceptual role. Systems like Apache Spark and similar tools like Apache Flink for pure streaming enable huge datasets to be processed in parallel across clusters of computers. Analogy. Instead of one large factory assembly line processing all raw materials sequentially, a single powerful server, distributed processing, is like having hundreds or thousands of smaller, coordinated workshops working simultaneously on different parts of the same large batch of raw materials. Key idea: data is automatically partitioned and distributed across workers in the cluster. Tasks are sent to these workers. If a worker fails, the system ideally reschedules its tasks on another worker. This provides both massive scalability and fault tolerance. They can perform operations like filtering, joining, aggregating, and machine learning at scale. For audiobook formatting, we emphasize the concept of distributed computation rather than showing code. Real-time stream processing engines, e.g., Apache Flink. While Spark can handle streaming, dedicated stream processing engines like Apache Flink are built from the ground up for continuous computations over unbounded streams of data with very low latency. Conceptual role: they allow for continuous transformations, aggregations, and analysis of data as it arrives, enabling immediate insights and reactions. They are often used alongside event streaming platforms like Kafka. Key features: support for various windowing functions, e.g., aggregating data over the last 5 minutes, event time processing, handling out-of-order events, and stateful computations, remembering past events. Cloud-managed services versus self-managed clusters. Modern architectures often choose between cloud-managed services, highly abstracted services offered by cloud providers, e.g., Databricks, Amazon EMR, Google Cloud Dataflow, Azure Synapse Analytics. The cloud provider handles infrastructure provisioning, scaling, patching, and maintenance. Pros: lower operational overhead, faster deployment, automatic scaling, pay-as-you-go pricing. Cons: less control over underlying infrastructure, potential for vendor lock-in. Self-managed clusters, deploying and managing open-source frameworks like raw Apache Spark or Flink on your own servers or cloud virtual machines. Pros: full control, maximum customization, no vendor lock-in. Cons: higher operational burden, requires significant expertise to maintain, patching, and scaling. Serverless compute for transformations. Serverless functions, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, can be invaluable for event-driven data transformations. Conceptual role. A function is triggered by an event, e.g., a new file arriving in a data lake, a message in a queue. The cloud provider automatically provisions the necessary compute, runs the code, and scales automatically, and you only pay for the execution time. Benefits: extremely cost-effective for intermittent or event-driven workloads, zero operational overhead for managing servers. 5.5 Workflow orchestration and scheduling. As data pipelines become more complex, involving multiple stages, different processing engines, and numerous dependencies, effective workflow orchestration becomes essential. Orchestration tools define, schedule, monitor, and manage the execution of these data workflows. Why orchestration is critical: dependency management. Ensuring that a processing step doesn't start until all its preceding steps, e.g., data ingestion, have successfully completed. Scheduling, running pipelines at specific times or intervals, e.g., every hour, daily at midnight. Monitoring and alerting, providing a centralized view of pipeline status, identifying failures, and sending alerts. Retries and backfills, automatically retraying failed tasks and capabilities to rerun historical data. Operational visibility, offering a dashboard where teams can see the status of all data pipelines, pinpoint bottlenecks, and diagnose issues. Concepts of directed acyclic graphs, DAGs. Many orchestration tools use the concept of a directed acyclic graph, DAG, to define workflows. Conceptual definition. A DAG is a collection of nodes, tasks, and directed edges dependencies, where there's no way to start at one node and follow a sequence of edges back to that same node, i.e., no cycles. This neatly represents data pipelines. Tasks are steps, and edges define the order of execution. Example: Task A must complete before Task B can start. Conceptual tools: Apache Airflow, a widely adopted open-source platform for programmatically authoring, scheduling, and monitoring workflows. It defines workflows as Python code that creates. It provides a visual UI to monitor runs and manage tasks. Other tools like Prefect or Dagster offer similar capabilities, each with slightly different approaches to defining and managing workflows. Imagine a large global logistics company processing data from millions of real-time shipment updates, daily warehouse inventory reports, and weekly customs declarations. Without robust orchestration, it would be a nightmare to ensure that the weekly customs report, which needs processed data from all other sources, runs only after all necessary daily and real-time feeds have been accurately processed and transformed. An orchestration tool manages these dependencies, providing visibility and ensuring the timely and accurate delivery of critical business intelligence. The transformation and orchestration layers are where raw data truly begins its journey to becoming a strategic asset. By meticulously designing these processes, data architects ensure that the generated insights are not only accurate but also delivered efficiently and reliably, powering critical business decisions. Chapter 6: Serving the Demand. Data Access and Consumption Patterns. 6.1 Making Data Discoverable and Accessible. Even the most meticulously structured, cleaned, and transformed data is useless if it cannot be found, understood, or accessed by those who need it. In the context of big data, where volumes are vast and sources are diverse, the challenge of helping users find the right data is immense. This is where concepts like data discoverability and accessibility become paramount. The dark data challenge. Many organizations suffer from dark data, data that is collected, processed, and stored but never utilized for real insights because no one knows it exists, where it is, what it means, or how to use it reliably. This represents wasted effort and missed opportunities. The critical role of data catalogs. A data catalog is to an organization's data assets what a library catalog is to its books. It's an organized inventory of all data assets across the enterprise, providing metadata data about data, context, and lineage. Conceptual explanation. A data catalog typically serves as a central hub where users can search for datasets, understand their meaning, e.g., through business glossaries and definitions, See their source and transformation history, data lineage, view data quality metrics, and identify data owners or subject matter experts. Imagine a single place where an analyst can not only find a customer sales dataset, but also understand what each column means, know where the data originated, see when it was last updated, and even find out who to contact for more information. Benefits: enhanced discoverability. Users can easily find relevant data for their analytical needs. Improved trust. Understanding data lineage and quality metrics builds confidence in the data. Reduced duplication. Prevents multiple teams from creating similar datasets. Faster time to insight. Analysts spend less time searching for and validating data. Facilitates governance. Provides a foundation for data governance policies and compliance. Data portals and marketplaces. Beyond just catalogs, some organizations implement data portals or marketplaces. These are user-friendly interfaces where validated, curated data products can be published, subscribed to, and consumed by various teams. This promotes a self-service model for data access, much like an internal app store for data. Importance of documentation and data dictionaries. Even without a full-blown data catalog, clear and comprehensive documentation is vital. Data dictionaries define schema, data types, and brief descriptions for each field within a dataset. READMEs for datasets, process documentation for pipelines, and architectural diagrams should be standard practice. 6.2 Consumption patterns. Getting data to users. Once data is discoverable and ready, it needs to be delivered to diverse users and applications in formats they can readily consume. The way data is served fundamentally shapes how an organization derives value from its data. Business intelligence, buy, and reporting. This is perhaps the most common consumption pattern, aimed at providing an understanding of past and present business performance. How it works: data from data warehouses, data marts, or curated layers in data lakes/lakehouses is accessed by buy tools. These tools allow users to create dashboards, reports, and interactive visualizations. Conceptual tools. Market leaders like Tableau, Microsoft Power BI, and Google Looker, formerly Data Studio, provide intuitive interfaces for data exploration, drag-and-drop report building, and self-service analytics, enabling business users to answer their own questions. Best for performance monitoring, trend analysis, operational reporting, and strategic decision-making based on aggregate historical data. Programmatic access, APIs. For applications, microservices, or external partners, data is often consumed programmatically via APIs, application programming interfaces. How it works. Data architects design and expose well-documented APIs, e.g., REST-TFL APIs, GraphQL, that allow other software systems to request and receive specific datasets or aggregated insights. Best for enabling data-driven features within customer-facing applications, integrating with partner systems, or powering internal operational tools transparently. Data science workbenches and notebooks. Data scientists and machine learning engineers often require direct, granular access to process data for advanced analytics, model training, and experimentation. How it works. They use specialized environments, often cloud-based, or tools like Jupyter notebooks, connected directly to data lakes or analytical data stores. These environments allow them to write code, Python, R, Scala, to query, manipulate, and analyze data without the constraints of pre-built reports. Best for exploratory data analysis, EDA, feature engineering for machine learning, developing predictive models, and complex statistical analysis. Data feeds and exports. For large-scale data sharing, either internally or externally, data can be provided as scheduled feeds or bulk exports in common formats like CSV, Parquet, or JSON. Best for sharing data with external vendors, feeding downstream systems that require batch updates or regulatory reporting. 6.3 Integrating data architecture with machine learning, ML, workflows. Machine learning's ascent has profound implications for data architecture. ML models are fundamentally data-hungry, and their effectiveness is directly tied to the quality and accessibility of the data they consume. Modern data architectures must seamlessly support the entire ML lifecycle, often referred to as ML ops. ML data preparation. Need. ML models require vast amounts of curated data for training and testing. This data needs to be clean, feature-engineered, and often specifically formatted. Architectural role. The data architecture must provide robust pipelines to extract, transform, and load data into specialized feature stores, repositories for pre-computed, reusable features, or data warehouses optimized for ML training. Data versioning, tracking which data was used to train a specific model, is also critical for reproducibility. ML model serving. Need. Once models are trained, they need to be deployed and served with real-time or batch data for making predictions inference. Architectural role. This often involves exposing APIs that client applications can call to send new data and receive predictions. The architecture needs to handle high concurrency, low latency requirements, and potentially stream processing for real-time inference, e.g., fraud detection, along with the capability to manage batch inference for large datasets. ML ops considerations. Just like DevOps for software development, ML ops focuses on standardizing and streamlining the ML lifecycle. From a data architecture perspective, this means data versioning, tracking changes to datasets used for training and inference, ensuring reproducibility and debugging. Data lineage, understanding the journey of data from source to ML model output. Model monitoring, continuously monitoring the performance of deployed models, including detecting data drift, where the characteristics of incoming data change over time, degrading model accuracy. Imagine a financial institution using ML for real-time fraud detection. Its data architecture continually streams transactional data, which is immediately cleaned and feature-engineered, data preparation. This data is then fed to deployed ML models via a low-latency API to instantly score transactions for risk model serving. The architecture also monitors the data flowing into these models for any shifts that might indicate a new fraud pattern emerging, ML ops consideration, allowing for quick model retraining. 6.4. The rise of reverse ETL. Historically, data flowed predominantly in one direction, from operational systems to analytical systems. Insights were generated in data warehouses or lakes, informing business decisions, but remained separate from the operational applications that directly interacted with customers. Reverse ETL describes the relatively new, but rapidly growing, paradigm of moving refined, aggregated, or derived data back into operational source systems. Definition. It is the process of taking data that has been transformed and enriched in a data warehouse, data lake, or analytical platform, and pushing it back into SaaS applications, like CRM, ERP, marketing automation, support tools, or transactional databases. Use cases, customer personalization, pushing segment information or churn risk scores from the data warehouse back into a marketing automation platform to trigger personalized campaigns. Sales enablement, updating a CRM system with a customer's lifetime value, product recommendations, or predicted next best action, directly visible to sales representatives. Customer support, populating a customer support tool with a customer's entire purchase history and sentiment scores for a more informed support agent. Product analytics, sending user behavior aggregates from the data warehouse back to a product management tool to inform feature development. Benefits, closes the loop between insights and action, ensures all operational teams have access to the latest, most relevant, and enriched data, and makes data actionable in the tools that business users already employ daily. 6.5. Performance, security, and scalability in the serving layer. The serving layer is the organization's data storefront, and as such, it demands high performance, robust security, and the ability to scale seamlessly. Optimizing query performance, data formats, using columnar storage formats like Parquet or Orc for analytical data as they are optimized for fast analytical queries. Indexing and partitioning, strategically applying indexes to frequently queried columns and partitioning large datasets, e.g., by date or region, to reduce the amount of data scanned. Caching, implementing caching layers for frequently accessed data or pre-computed aggregates to reduce query latency. Query optimization, writing efficient SQL queries and utilizing query execution plans to identify and resolve bottlenecks. Implementing granular security. Access control. Beyond basic user authentication, implementing fine-grained authorization, e.g., row-level security, column-level security, to ensure users only see the data they are authorized for. For example, a sales manager should only see data for their region, and a buy analyst shouldn't see personally identifiable information, PII, unless explicitly given access. Data masking/anonymization. For sensitive data, ensuring that it is masked or anonymized before being exposed to end users or applications unless absolutely necessary and authorized. Auditing. Maintaining detailed logs of who accessed what data and when, crucial for security monitoring and compliance. Ensuring scalability. The serving layer must be able to handle fluctuating demand, whether from a surge in dashboard users, a spike in API calls, or a sudden need to run a large batch inference job. Elastic scaling, leveraging cloud services that can automatically scale compute and storage resources up or down based on load, ensuring consistent performance without over-provisioning. Load balancing, distributing incoming requests across multiple servers or instances to prevent any single point of failure or overload. By meticulously designing the data access and consumption patterns, organizations can ensure that their data architecture not only stores and processes information effectively, but also truly empowers every part of the business to leverage data for innovation, efficiency, and competitive advantage. Chapter 7, The Guardians, Data Governance, Quality, and Security. 7.1, The Unsung Heroes, Why Governance is Paramount in Big Data. Imagine a city without traffic laws, zoning regulations, or building codes. Chaos would ensue, traffic jams, unsafe structures, and uncontrolled sprawl. Similarly, in the world of data, without robust governance, chaos is inevitable. Data becomes inconsistent, unreliable, risky, and ultimately unusable. Data governance is the overarching framework of policies, processes, roles, and standards for managing an organization's data assets. It's not just about technology. It's about people, accountability, and the rules of engagement for all data within the enterprise. In the context of big data, with its immense volume, velocity, and variety, data governance transforms from a nice-to-have to a non-negotiable imperative. The consequences of poor data governance are severe and far-reaching. Non-compliance and legal risks. Failure to adhere to data privacy regulations, GDPR, CCPA, HIPAA, can lead to massive fines, legal battles, and reputational damage. Data breaches and security incidents. Without clear policies on data access, encryption, and handling of sensitive information, organizations become vulnerable to cyber attacks and insider threats. Distrust in data and flawed decisions. If data is inconsistent or of poor quality, business leaders lose faith in analytical insights, leading to decisions based on gut feeling rather than evidence. Inefficiency and operational waste. Teams spend valuable time trying to find, validate, or reconcile inconsistent data, leading to duplicated efforts and reduced productivity. Lost opportunities. An inability to leverage data effectively for new products, services, or market insights means falling behind competitors. Conversely, strong data governance builds confidence, cultivates a data-driven culture, and underpins all efforts to extract value from data. It ensures that data is reliable, secure, compliant, and understood by everyone who uses it. 7.2 Ensuring data quality, trustworthiness by design. Data quality is the bedrock of reliable insights. If the underlying data is flawed, any analysis derived from it, no matter how sophisticated, will also be flawed. This is often summarized as garbage in, garbage out. Data governance provides the framework, and data quality provides the specific actions to ensure data's fitness for use. Dimensions of data quality. To assess and improve data quality, it's helpful to consider its key dimensions. Accuracy. Does the data reflect reality? Is the customer's address correct? Is the sales figure precise? Completeness. Is all necessary data present? Are there missing values where there shouldn't be? Consistency. Is the data consistent across different systems and over time? Is a customer ID meaning the same thing everywhere? Are units of measurement standardized? Timeliness. Is the data available when needed? Is it fresh enough for the task at hand? E.g., real-time for fraud detection, daily for reporting. Validity. Does the data conform to defined standards, formats, or business rules? Is a phone number in the correct format? Is a product code from a valid list? Uniqueness. Are there duplicate records that should be distinct? Data quality frameworks and remediation. A robust data architecture bakes data quality checks directly into the data pipelines. This often involves data profiling, analyzing source data to understand its structure, content, and quality characteristics, e.g., value distributions, null percentages, patterns. Validation rules. Implementing automated checks at ingestion and transformation stages to ensure data conforms to expected formats and business rules. Monitoring and alerting. Continuously monitoring data quality metrics and alerting data owners or quality stewards when thresholds are breached. Remediation processes. Establishing clear procedures for resolving data quality issues, either through automated cleansing or manual intervention. One common anecdote illustrates the vital role of data quality. A multinational company once launched a major global marketing campaign based on a report that significantly overestimated their market share in a key region. Later, it was discovered that the underlying data issue was a simple, yet pervasive, error where a single entry error, a duplicated country code, led to the exaggerated numbers. This costly mistake highlights how seemingly minor data quality issues can lead to profound strategic missteps. Building data quality in from the design phase, not just as an afterthought, is essential. 7.3 Master Data Management, MDM, and Reference Data Management, RDM. For organizations to have a consistent and reliable view of their core business entities, Master Data Management, MDM, and Reference Data Management, RDM, are crucial components of data governance. Master Data Management, MDM, purpose: to create a single, consistent, and accurate master record for critical business entities that are shared across the enterprise. These entities typically include customers, products, suppliers, financials, and locations. Challenge: in large organizations, the same customer might appear in a CRM system, an ERP system, and an e-commerce platform, each with slightly different details or identifiers. Without MDM, this fragmentation leads to inconsistent reporting, inefficient processes, and a fractured view of the customer. How it works conceptually. MDM involves processes and technologies to match, merge, and deduplicate these records, creating a golden record or single source of truth for each master data entity. This master record is then distributed to or referenced by all systems needing that information. Benefit: enables a true 360-degree view of customers, products, or suppliers, improving operational efficiency, reporting accuracy, and customer experience. Reference Data Management, RDM, purpose: to manage and distribute standardized codes and descriptions that are used across multiple systems to categorize or classify data. Examples include country codes, currency codes, units of measure, product categories, gender codes, or employee status types. Challenge: inconsistent reference data, e.g., US versus USA versus United States for the same country, can lead to data integration failures and reporting discrepancies. How it works conceptually. RDM establishes a central repository for these codes, ensures their accuracy, and propagates them consistently to all systems that rely on them. Benefit: ensures data consistency, simplifies data integration, and improves data quality across the enterprise. 7.4 Fortifying the Fortress, Data Security. Data security in modern big data architectures is a multi-layered, continuous process. It's about protecting data from unauthorized access, accidental destruction, and malicious attacks throughout its entire lifecycle. Conceptual security layers, network security, protecting the perimeter and internal network segments, e.g., firewalls, virtual private clouds, network segmentation. Identity and Access Management, IAM, authenticating users and systems, and authorizing what resources they can access. Role-based access control, RBAC. Users are assigned roles, and roles have specific permissions, e.g., data analyst role can read, data engineer role can read-write. Attribute-based access control, ABAC. More granular control based on user attributes, e.g., department, location, and data attributes, e.g., sensitivity classification. A user can only access sensitive data if they are in a specific department and have appropriate clearance. Data encryption, data at rest. Encrypting data when it's stored on disk, e.g., in data lakes, databases. This protects data even if the storage medium is physically compromised. Data in transit. Encrypting data as it moves across networks, e.g., between applications, to storage, over the internet, using protocols like TLS-SSL. Data masking, tokenization, anonymization. Techniques used to protect sensitive information while still allowing for analysis or testing. Masking, replacing sensitive data with realistic, but fictional, data, e.g., replacing real credit card numbers with dummy numbers for testing environments. Tokenization, replacing sensitive data with a randomly generated non-sensitive equivalent, a token that can be swapped back for the real data only by authorized systems. Anonymization, removing or scrambling personally identifiable information, PII, so that individual data subjects cannot be re-identified. Auditing and logging, continuously logging all data access, modification, and administrative actions. These logs are critical for security monitoring, detecting suspicious activities, and forensics in case of a breach. 7.5. Navigating the regulatory landscape. Data privacy and compliance. The regulatory landscape around data privacy is becoming increasingly complex and stringent globally. Data architects must design systems that are compliant by default. Overview of major global regulations. GDPR, General Data Protection Regulation. Europe's landmark privacy law, focusing on protecting individuals' personal data. It introduced concepts like data portability, the right to be forgotten, and strict consent requirements. CCPA, California Consumer Privacy Act, California Privacy Rights Act. Similar to GDPR, but for California residents, granting consumers more control over their personal information. HIPAA, Health Insurance Portability and Accountability Act. Specific to the U.S. healthcare sector, setting standards for protecting sensitive patient health information. Many other region-specific laws, e.g., LGPD in Brazil, POPIA in South Africa, PIPEDA in Canada, continue to emerge, indicating a global trend towards stronger data protection. Privacy by design principles. This principle, fundamental to GDPR and increasingly adopted globally, means embedding privacy safeguards into architectural decisions from the very beginning, rather than adding them as an afterthought. Key aspects include data minimization, only collecting and storing the minimum amount of data necessary for a specific purpose. Purpose limitation, using collected data only for the explicit purposes for which it was gathered. Data de-identification, employing anonymization or pseudonymization techniques where possible. Transparency, clearly informing individuals about how their data is collected, used, and protected. Data retention policies, defining and enforcing policies for how long different types of data can be stored, and ensuring secure deletion once retention limits are met. Ensuring auditability and accountability. Data architectures must provide comprehensive audit trails to demonstrate compliance to regulators. This includes tracking user consent, data lineage, to show where data came from and how it was transformed, and access logs. A healthcare institution, for example, built its data architecture with HIPAA compliance as a core design principle. This meant encrypting all patient data at rest and in transit, implementing strict, fine-grained access controls, ensuring only authorized personnel could view specific patient records, and maintaining detailed audit logs of every data access, which could be reviewed for compliance audits. Building a culture of data stewardship across the organization is key. Data governance, quality, and security are not merely technical responsibilities, but shared organizational mandates. The data architect, as a guardian of the data, plays a pivotal role in designing systems that embody these principles, ensuring that data is an asset, not a liability. Chapter 8. Architectural Paradigms for the Modern Enterprise. The landscape of data architecture is in constant flux, driven by technological innovations, evolving business demands, and the sheer scale and complexity of managing big data. Beyond selecting individual tools, modern data architects must understand and strategically apply overarching architectural paradigms, conceptual frameworks that guide the design and implementation of data systems. This chapter explores some of the most influential paradigms shaping today's data strategies. 8.1. The Cloud-Native Data Architecture Revolution. Perhaps the most significant shift in data architecture over the last decade has been the move to the cloud. Cloud-native data architectures are built to leverage the unique advantages of cloud computing platforms rather than adapting traditional on-premise designs. This isn't just about moving servers to a remote data center. It's about fundamentally rethinking how data systems are built, operated, and scaled. Advantages of cloud-native data architectures: elasticity and limitless scalability. Cloud resources can be provisioned and deprovisioned almost instantly. This means data storage and processing power can scale up or down automatically in response to demand, preventing bottlenecks during peak loads and reducing costs during idle periods. Imagine a Black Friday sales surge. Cloud resources can effortlessly accommodate hundreds of thousands of concurrent users and transactions, then dial back down on an average Tuesday. Leveraging managed services, reduced operational burden. Cloud providers offer a vast array of fully managed services for data ingestion, storage, processing, analytics, and machine learning, e.g., managed data warehouses, lakehouses, streaming platforms, serverless compute. This offloads the operational overhead of managing underlying infrastructure, servers, patching, backups, scaling, to the cloud provider, freeing up valuable internal engineering resources to focus on business-specific solutions. Global reach and proximity. Cloud regions and availability zones distributed worldwide enable data architects to place data and services physically closer to users, reducing latency and improving user experience. This is vital for global organizations. Favorable cost models, pay-as-you-go. Instead of large upfront capital expenditures for hardware, cloud computing operates on an operational expenditure (OpEx) model, where you pay only for the resources you consume. This allows for experimentation and rapid iteration without significant upfront investment. Disadvantages and considerations. Potential vendor lock-in. Relying heavily on proprietary managed services from a single cloud provider can make it challenging and costly to migrate to a different provider later. Cost management complexity. While pay-as-you-go is powerful, optimizing cloud spend in complex data architectures requires careful monitoring and control, as costs can easily escalate if not managed correctly. Migration challenges. Moving existing on-premise data systems to the cloud, especially monolithic legacy applications, can be a complex and time-consuming endeavor. Conceptual overview of major cloud data ecosystems. All major providers, Amazon Web Services/Oz, Microsoft Azure, Google Cloud Platform/GCP, offer comprehensive, integrated suites of data services spanning all layers of the data architecture. While their specific service names differ, e.g., AWS S3, Redshift, Kinesis, Glue, Azure ADLS, Synapse, Event Hubs, Data Factory, GCP GCS, BigQuery, PubSub, Dataflow, they all provide conceptual equivalents for object storage, data warehousing/lakehouse, event streaming, data integration, and analytical processing. Understanding their conceptual role in the architecture is more important than memorizing every service name. Hybrid and multi-cloud considerations. Hybrid cloud. Combining on-premise infrastructure with public cloud resources. This is common for organizations with strict regulatory requirements, existing significant on-premise investments, or data locality needs. Multi-cloud. Using services from multiple public cloud providers. Reasons include avoiding vendor lock-in, leveraging best-of-breed services from different providers, or meeting specific regulatory requirements for data sovereignty. Multi-cloud architectures introduce complexity in data integration, security, and governance. 8.2 Serverless data processing, abstraction and efficiency. Building on the cloud-native paradigm, serverless data processing takes abstraction to another level. The term serverless is a bit of a misnomer. There are still servers, but the cloud provider fully manages them, abstracting away all server management from the user. Definition: with serverless, you write code, and the cloud provider automatically provisions, scales, and manages the underlying compute infrastructure. You pay only for the actual computation time and memory consumed, often down to the millisecond. How it works: conceptual example. You might configure a serverless function to be triggered whenever a new file lands in your data lake. The function executes, processes the file, and then shuts down, incurring cost only for the execution duration. Use cases in data architecture. Event-driven transformations, transforming data as soon as an event occurs, e.g., new file uploaded, message in a queue. Lightweight APIs, providing low-latency data access APIs. Data validation, running quick quality checks on incoming data. Periodic batch jobs, running small, scheduled tasks where provisioning a full cluster would be overkill. Benefits: zero operational overhead. No servers to provision, patch, or scale manually. Automatic scaling, handles unpredictable spikes in traffic without manual intervention. Cost efficiency, highly cost-effective for intermittent or variable workloads, as you only pay for actual execution. Limitations: cold starts. Initial requests to a dormant function might experience a slight delay. Execution duration limits. Functions typically have time limits on how long they can run. Vendor lock-in, often tied to specific cloud provider ecosystems. Debugging complexity. Debugging issues in a distributed serverless environment can be more challenging than in traditional server-based systems. 8.3 Data mesh, decentralizing data ownership. For large, complex organizations with many business domains, a centralized data architecture can become a bottleneck. The data mesh paradigm, pioneered by Zhamak Dehghani, offers a revolutionary approach by advocating for decentralized data ownership and treating data as a product. Core principles of data mesh: domain-oriented ownership. Instead of a central data team owning all data, data ownership and responsibility are decentralized to the business domains that produce and consume the data. For example, a customer domain team owns the customer data, not a central data engineering team. Data as a product. Data within each domain is treated as a product, meaning it must be discoverable, addressable, trustworthy, self-describing, interoperable, and valuable to its consumers. Domain teams are responsible for the quality, reliability, and usability of their data products. Self-serve data platform. A central data platform team provides common infrastructure, tools, and capabilities, e.g., data storage, processing engines, governance tools, that domain teams can use to build and serve their data products without having to build everything from scratch. Federated computational governance. While ownership is decentralized, there's a strong emphasis on consistent governance. A small, central governance body defines global rules and policies, e.g., data privacy standards, interoperability conventions, which are then technically enforced and implemented by each domain team. This balances autonomy with necessary control. Benefits of data mesh. Scales insights significantly, eliminates bottlenecks in central data teams, allowing the organization to derive value from data much faster. Reduces central bottlenecks. Central data teams are no longer responsible for every data pipeline or dataset. Fosters team autonomy and innovation. Domain teams have the autonomy to build data products tailored to their specific needs. Improves data quality at the source. Since data producers, domain teams, are responsible for their data products, quality tends to improve. Enables cross-domain data access. Data products are designed for easy consumption by other domains. Challenges. Significant cultural shift. Requires a fundamental transformation in organizational structure, mindset, and incentives, often more challenging than the technical implementation. Initial platform complexity. Building the self-serve data platform requires significant upfront investment and expertise. Governance implementation. Ensuring consistent application of federated governance across many teams can be tricky. Imagine a large enterprise with numerous independent business units: retail, supply chain, marketing, finance. A traditional centralized data team would struggle to meet the diverse and rapidly changing data needs of all these units. With a data mesh, the retail unit would be responsible for its customer order data product, making it available and well documented for other units, while the supply chain unit would manage its inventory data product. This empowers each unit to act as a data provider and consumer. 8.4 Data Fabric, Unified Access and Intelligence. While Data Mesh focuses on decentralized ownership, Data Fabric approaches the challenge of connecting disparate data sources from a different angle. Comprehensive, virtualized data access and integration. Definition: a data fabric is a unified, intelligent data management platform that integrates data from disparate sources, regardless of where the data resides, focusing on providing seamless, secure data access and discovery. It's less about reorganizing teams and more about creating a technology overlay to unify data across organizational silos. Key components: conceptual, data integration capabilities. Connecting to a vast range of data sources, on-premise, cloud, various databases, streams. Robust data governance. Centrally managed policies for security, privacy, and quality applied consistently across all integrated data. Metadata management and knowledge graphs. Using metadata and powerful graph technologies to understand relationships between data assets, enabling intelligent discovery and automated data flow recommendations. Data virtualization. The ability to query data from multiple sources as if it were a single logical data source, without physically moving or duplicating the data. Data pipelines automation and orchestration. Intelligent automation of data integration, transformation, and delivery. Semantic layer. A business-friendly representation of underlying data, making it easier for non-technical users to access and understand information. Focus. The data fabric emphasizes creating a unified experience for data access, discovery, and governance, primarily through technological means, often leveraging AI and machine learning to automate data integration and management tasks. It's about intelligently connecting everything. Benefits: simplified data access. Users can access data from across the enterprise through a single point without needing to know specific locations or formats. Unified data view. Provides a holistic view of enterprise data, regardless of its underlying storage. Enhanced discoverability. Metadata and knowledge graphs enable intelligent data discovery. Reduced data movement. Less data duplication and movement, which saves costs and improves data freshness. Faster time to market. Accelerates the development of data-driven applications and analytics. Comparison to data mesh. Complementary, not mutually exclusive. While data mesh emphasizes decentralized ownership and cultural shift, data fabric focuses on leveraging technology, like advanced metadata management and virtualization, to provide a unified access layer over potentially distributed data sources. A data mesh could use data fabric technologies to implement its self-serve platform and federated governance. A data fabric could apply to a centralized organization, unifying existing silos. 8.5 When to choose which paradigm. A decision framework. There is no one-size-fits-all architectural paradigm. The choice depends on several factors: organizational structure and culture. Is your organization prepared for significant cultural and organizational change, data mesh? Or does a centralized, technology-driven integration make more sense, data fabric? Business needs and scale. Are you struggling with bottlenecks due to a monolithic data team, data mesh? Do you need to connect a highly distributed, heterogeneous data landscape, data fabric? Existing infrastructure and debt. What degree of legacy systems do you need to integrate? Cloud-native strategies often simplify new builds but require careful migration for existing systems. Budget and resources. Implementing any of these paradigms requires significant investment in technology, talent, and time. Regulatory environment. Specific regulations might influence decisions around data locality, privacy, and governance. Many organizations adopt these paradigms evolutionary rather than through a big bang. For instance, a company starting its cloud journey might first focus on solidifying its cloud-native architecture, then gradually build towards a lakehouse on that platform. As they grow, they might later consider implementing data mesh principles to decentralize data ownership, or adopt a data fabric to unify diverse data sources. Understanding these architectural paradigms allows data architects to guide their organizations through the complex journey of becoming truly data-driven, choosing the right paths to unlock value from their big data assets. Chapter 9, The Data Architect's Toolkit, Technologies and Ecosystems. In the rapidly evolving world of data architecture, new tools and technologies emerge constantly. It's easy to get lost in the sheer volume of vendor names, open-source projects, and cloud services. However, a skilled data architect understands that tools are merely means to an end. The true art lies in understanding the conceptual role each tool plays within the overall data ecosystem, and selecting the right combination to meet specific business needs. This chapter provides a conceptual overview of the essential categories of tools in the modern data stack, emphasizing their function rather than deep technical details, making it accessible for both print and audio. 9.1. Categorizing the modern data stack. Rather than listing every possible product, it's more productive to think in terms of functional categories. Each category addresses a particular stage or requirement within the data lifecycle, as discussed in Chapter 2. Many tools may span multiple categories, offering integrated capabilities, but understanding their primary purpose helps in making informed architectural decisions. We can broadly categorize the modern data stack into data ingestion and streaming, data storage solutions, data processing and transformation, orchestration and workflow management, data access and presentation, data governance and catalogs. 9.2. Data ingestion and streaming tools, concepts. These tools are at the very beginning of the data pipeline, responsible for bringing data into the system. Their primary focus is on scalability, reliability, and handling high volumes and velocities of data. Message brokers/event streaming platforms, conceptual role. These act as central hubs for high-volume, real-time data streams. They enable applications, data producers, to publish streams of events, e.g., website clicks, sensor readings, financial transactions, without needing to know which other applications' data consumers will use that data. They provide durable storage for these event streams, allowing multiple consumers to read data at their own pace and replay historical events if needed. How it works, simplistic analogy. Imagine a highly efficient, endlessly long conveyor belt that transports messages. Producers place messages onto the belt, and consumers can pick them up from any point. If a consumer needs to process something again, they can rewind and start from an earlier point. Prominent examples: Apache Kafka, the open-source standard, Amazon Kinesis, Azure Event Hubs, Google Cloud PubSub. All provide similar capabilities in their respective cloud ecosystems. Stream processing engines. Conceptual role. These tools process data continuously as it flows through the message brokers, performing transformations, aggregations, and analysis in real time or near real time. How it works, simplistic analogy. As items move on the conveyor belt, event stream, these engines act like automated sorting and packaging machines that continuously work on each item as it passes, rather than waiting for a large batch to accumulate. Prominent examples: Apache Flink, Spark Streaming, part of Apache Spark. Managed data integration services, conceptual role. These services simplify the process of connecting to various data sources, including databases, SaaS applications, and APIs, and loading data into a data warehouse or data lake. They often include pre-built connectors and handle tasks like schema mapping and incremental updates. Prominent examples: Fivetran, Stitch, Matillion, and cloud-native services like AWS Glue for ETL job creation, Azure Data Factory, Google Cloud Dataflow. 9.3. Data storage solutions, concepts. As discussed in Chapter 4, the choice of storage depends heavily on data type, access patterns, and performance needs. Modern architectures often use a mix of these. Cloud object storage, conceptual role, the foundational layer for data lakes. These services provide massively scalable, highly durable, and cost-effective storage for any type of data: files, images, videos, logs, structured data in file formats like Parquet. Data is stored as objects in buckets. It's the ultimate dumping ground for raw data. Prominent examples: Amazon S3, Azure Data Lake Storage, ADLS Gen 2, Google Cloud Storage GCS. Cloud data warehouses. Conceptual role: highly optimized analytical databases built for the cloud. They allow organizations to store vast amounts of structured and increasingly semi-structured data and query it with incredible speed using standard SQL. They typically separate compute and storage, allowing them to scale independently. How it works: key advantage: you can store terabytes of data, but only pay for the compute resources you use when running queries. If your query load drops, your compute costs drop too. Prominent examples: Snowflake, Google BigQuery, Amazon Redshift, Azure Synapse Analytics. NoSQL databases, conceptual categories, document databases. Store data in flexible, JSON-like documents, ideal for rapidly evolving schemas, e.g., MongoDB, Amazon DocumentDB, Azure Cosmos DB Document API. Key value stores. Simple, high-performance databases for storing data as key-value pairs. Great for caching or session management. E.g., Redis, Amazon DynamoDB, Azure Cosmos DB Table API. Column family databases. Designed for very large, distributed datasets with high write throughput. E.g., Apache Cassandra, Apache HBase, Amazon DynamoDB Column API. Graph databases. Optimized for storing and querying relationships between data points. E.g., Neo4j, Amazon Neptune, Azure Cosmos DB Graph API. Open table formats for data lakes. Conceptual role. These innovative technologies extend the capabilities of standard data lakes by adding features traditionally found in databases: ACID transactions, schema evolution, time travel. They turn a collection of files into queryable tables. Prominent examples: Delta Lake, Apache Iceberg, Apache Hudi. 9.4 Data processing and transformation engines, concepts. These are the workhorses that manipulate and refine data, creating the cleaned and curated datasets necessary for analysis. Distributed computing frameworks. Conceptual role: designed to process massive datasets in parallel across clusters of machines. They provide powerful APIs to perform transformations, joins, aggregations, and even run machine learning algorithms on diverse data types. They are versatile, supporting both batch and streaming workloads. How it works without code. Instead of processing data on a single supercomputer, these frameworks break tasks into smaller pieces, distribute them across many ordinary computers, and then combine the results. This allows for horizontal scalability. Prominent examples: Apache Spark, the de facto standard for general-purpose big data processing; Hadoop MapReduce, foundational, but often replaced by Spark for complexity; serverless compute for transformations. Conceptual role: as discussed, these are event-driven functions that execute short-lived, independent compute tasks, typically in response to a trigger, e.g., a new file arriving. Prominent examples: AWS Lambda, Azure Functions, Google Cloud Functions. Data transformation tools, declarative. Conceptual role: tools that enable data engineers to define data transformations using SQL or a declarative language, often encouraging modularity and testability. They are powerful for transforming data within data warehouses or lakehouses. Prominent examples: dbt, data build tool, which is used to model data using SQL, often turning tables into modular data pipelines. 9.5 Orchestration and workflow management, concepts. As pipelines become complex, these tools ensure tasks run in the correct order, manage dependencies, and provide visibility into the data workflow. Workflow orchestrators. Conceptual role: these systems define, schedule, monitor, and manage the execution of data pipelines as directed acyclic graphs, DAGs, of tasks. They allow data teams to build robust, fault-tolerant sequences of operations, handling retries, failures, and dependencies. Prominent examples: Apache Airflow open source, highly popular, Prefect, Dagster, and cloud-native orchestrators like AWS Step Functions, Azure Data Factory pipelines, Google Cloud Composer managed Airflow. 9.6 Data access and presentation tools, concepts. Once data is processed and refined, these tools make it consumable for various end users. Business intelligence, buy and visualization tools, conceptual role. These tools connect to data sources, allow users to create interactive dashboards, reports, and visualizations, and enable self-service data exploration. They are crucial for democratizing data access. Prominent examples: Tableau, Microsoft Power BI, Looker, Google Cloud, Qlik Sense. Data catalogs and governance platforms, conceptual role. These are central repositories for an organization's metadata, providing a searchable inventory of data assets, data lineage, business glossaries, and supporting data governance policies. They make data discoverable and help ensure compliance. Prominent examples: Alation, Collibra, Apache Atlas, AWS Glue Data Catalog. 9.7 Build versus buy decisions and open source versus commercial. A recurring theme in selecting tools is the build versus buy decision, often intertwined with the choice between open source solutions and commercial managed services. There's no universal best answer. Each approach has trade-offs crucial for a data architect to consider. Build your own open source. Pros: full control and customization, complete flexibility to tailor solutions to exact, niche requirements. No vendor lock-in. You own the code and can move it between infrastructure providers. Potential for cost savings, software licensing, no direct software license fees. Community support. Large open source projects often have vibrant communities, forums, and extensive documentation. Cons: high operational overhead. You are responsible for installation, patching, upgrades, maintenance, scaling, and ensuring high availability. This requires significant specialized internal expertise, e.g., managing a raw Apache Kafka cluster. Slower time to market. Building often takes longer than configuring a pre-built solution. Hidden costs. The cost of engineering time, specialized talent, and potential downtime can outweigh initial savings. When to choose? When you have highly specific, unique requirements that commercial products cannot meet, when very large scale requires extreme optimization, or when you have a strong, experienced internal operations team dedicated to managing these technologies. Buy commercial managed services. Pros: reduced operational overhead. The vendor cloud provider handles infrastructure management, patching, scaling, security, and maintenance. Faster time to market. Solutions are often ready to use with pre-built connectors and features. Feature richness. Commercial products often come with advanced features, support agreements, and SLAs, service level agreements. Focus on business value. Your internal teams can focus on data analysis and generating business insights rather than managing infrastructure. Cons: vendor lock-in. Can be difficult to migrate away from a particular vendor's proprietary offering. Less customization. May not perfectly fit every niche requirement. Cost: subscription fees or pay-per-use models can be higher than raw infrastructure costs, but this must be balanced against reduced operational expenses. When to choose? When speed of deployment is critical, when you have limited in-house operational expertise for highly complex distributed systems, when you need enterprise-grade support and SLAs, or when you want to minimize operational toil and focus resources on core business functions. Many organizations adopt a hybrid approach, using managed cloud services for foundational components, e.g., cloud object storage, managed data warehouses, while potentially deploying open-source solutions for specific custom processing tasks or specialized databases where greater control is needed. The data architect's role is to thoughtfully weigh these trade-offs, recognizing that the best tool is the one that most efficiently and effectively solves the business problem given the organization's unique constraints and capabilities. Chapter 10: Building for the Future. Design Principles, Best Practices, and Evolution. As we conclude our journey through the modern data architecture landscape, it's clear that the field is characterized by constant innovation and change. However, beneath the shifting technological surface lie enduring design principles and best practices that form the bedrock of successful data systems. This final chapter distills these universal truths, explores how to measure architectural success, delves into the evolving role of the data architect, and casts an eye towards future trends that will continue to shape this dynamic domain. 10.1 Common architectural patterns in practice. Over time, several recurring architectural patterns have emerged to address common big data challenges efficiently. Understanding these meta-patterns provides a framework for designing robust and adaptable systems. Lambda architecture, brief mention, concept. This pattern splits data processing into two distinct paths: a batch layer for comprehensive, accurate historical processing, and a speed layer for real-time, low-latency insights. The results from both layers are then merged in a serving layer. Benefit: offers a balance between accuracy from historical data and immediacy from real-time data. Challenge: can be complex to implement and maintain due to managing two separate code bases and merging results. Kappa architecture, brief mention, concept. A simpler alternative to Lambda, where all data is treated as a continuous stream. Batch processing is essentially replaced by reprocessing the stream from an earlier point when historical analysis or new logic is needed. Benefit: simplifies the architecture significantly by having a single processing path. Challenge: requires powerful stream processing capabilities and a durable, replayable message log. Medallion architecture, concept. As explored in Chapter 5, this is a layered approach often used within data lakes and lakehouses. It organizes data into progressively refined tiers: bronze layer, raw, untouched, immutable source data; silver layer, cleaned, conformed; cleaned, filtered, deduplicated, and conformed data, often integrated from multiple sources; gold layer, curated, aggregated; highly refined, aggregated, and business-ready data, modeled for specific consumption purposes, e.g., by dashboards, ML features. Benefit: promotes data quality, reusability, and traceability, making relevant data easier to find and trust for different user groups. Star snowflake schemas, revisited conceptually. Concept: these are traditional data modeling techniques used in data warehouses, particularly for dimensional modeling. They organize data into a central fact table containing measurements or metrics, surrounded by dimension tables containing descriptive attributes. A star schema has directly linked dimensions. A snowflake schema has normalized dimensions with subdimensions. Benefit: optimized for analytical queries, simplifies querying for business users, and facilitates easy aggregation. Relevance today. Even with data lakes, the gold layer products often conform to a star or snowflake-like structure for optimal by reporting. 10.2 Designing for non-functional requirements. Beyond meeting core business functions, a successful data architecture must also satisfy critical non-functional requirements, NFRs. These define how well the system performs and operates. Scalability, principle, design for anticipated growth in data volume, velocity, and user concurrency. Strategies: favor horizontal scaling, adding more machines over vertical scaling, making existing machines more powerful. Leverage cloud elasticity and managed services that scale automatically. Use distributed processing frameworks. Design data models that partition data efficiently. Resilience and fault tolerance. Principle: ensure the data system can withstand failures and recover gracefully without significant data loss or downtime. Strategies: implement redundancy, e.g., data replication across multiple availability zones. Design pipelines to be idempotent and rerunnable. Incorporate robust error handling and retry mechanisms. Plan for disaster recovery, backup and restore procedures, recovery point time objectives. Performance, principle, optimize for the speed and efficiency of data processing, querying, and delivery. Strategies: choose appropriate storage formats, e.g., columnar for analytics. Optimize data partitioning and indexing. Implement caching where appropriate. Write efficient queries. Separate compute from storage where possible. Right-size compute resources. Security revisited. Principle: embed security controls at every layer of the data architecture from inception. Strategies: zero trust principles, verify everything, assume nothing. Strong identity and access management, IAM with least privilege. Encryption of data at rest and in transit, regular security audits and vulnerability assessments. Adhering to DevSecOps principles, integrating security into the development pipeline. Cost optimization, principle, manage cloud spend efficiently while meeting performance and reliability targets. Strategies: understand cloud pricing models, compute, storage, network egress. Right-size resources to avoid overprovisioning. Leverage serverless and auto-scaling for variable workloads. Tier storage, move less frequently accessed data to cheaper storage classes. Optimize queries to reduce compute time. Implement data lifecycle policies, e.g., deleting old, unused data. 10.3 Measuring success. KPIs for data architecture. To justify investments and demonstrate value, data architects must be able to measure the success of their architectures. This involves tracking both technical and business-oriented key performance indicators, KPIs. Technical metrics, data quality levels, percentage of complete, accurate, consistent, and valid data. Pipeline latency, time from data ingestion to availability in the consumption layer. Pipeline reliability, percentage of successful pipeline runs, number of failures, and average time to recovery. System uptime availability, percentage of time the data platform components are operational. Query performance, average query execution time, concurrency limits, storage growth, how data volumes are increasing. Compute utilization, efficiency of resource usage. Business metrics. These are often harder to attribute solely to data architecture but demonstrate its enablement. Time to insight. How quickly can new business questions be answered or new dashboards be created? Data utilization rates. How many users are actively querying data? How many unique datasets are being consumed? Cost efficiency per data unit. Cost of storage or processing per terabyte, e.g., how much does it cost to deliver one insight? Enablement of new business initiatives. How many new products, services, or strategic insights were made possible by the data architecture? E.g., a modern data architecture enabled a new personalized marketing campaign that increased conversion rates by X%. Data user satisfaction. Surveys or direct feedback from data consumers on the usability and reliability of the data platform. The key is to link architectural improvements directly to tangible business outcomes, demonstrating how robust data foundations accelerate innovation and enhance decision-making. 10.4 The evolving role of the data architect. The role of the data architect is continuously expanding. No longer solely a technical expert focused on database design, the modern data architect is a multifaceted professional. Strategic advisor, translating complex business goals into concrete data strategies and architectural roadmaps. They understand the why behind the data. Cross-functional bridge builder, effectively communicating with diverse stakeholders, executives, business users, data scientists, software engineers, legal, and compliance teams. They translate technical complexities into business value and vice versa. Technology curator, staying abreast of emerging technologies, evaluating their fit for the organization, and making informed build vs buy and open source vs commercial decisions. Champion of data literacy and governance, advocating for data quality, security, and privacy across the organization, fostering a culture where data is a shared, trusted asset. Problem solver and innovator, identifying bottlenecks, designing solutions for complex data challenges, and driving continuous improvement in the data landscape. Their journey is one of continuous learning and adaptation. A successful modern data architect is not just an expert in databases or clouds, but a strategic enabler who understands the broader context of how data drives business value. Consider the data architect at a pioneering retail company. They didn't just design the new cloud data lakehouse. They championed its adoption to leadership, collaborated with marketing to integrate new customer interaction data, worked with the legal team to ensure privacy compliance, and continuously iterated on the architecture based on business team feedback. Their role was a blend of technical expertise, strategic vision, and cross-functional leadership. 10.5 Future Trends and Beyond. The trajectory of data architecture is towards ever-increasing automation, intelligence, and democratization. AI ML's continued impact on architecture. Automated data management. AI will further automate tasks like data quality checks, schema inference, data integration, and even resource provisioning and optimization. Intelligent data catalogs. AI-powered tools will make data discovery and understanding even more intuitive, recommending relevant datasets or suggesting connections. Explainable AI for data governance. AI will increasingly assist in ensuring compliance by identifying sensitive data patterns or flagging potential privacy violations. Maturity of data mesh and data fabric. These paradigms will continue to evolve, with more practical implementations and tooling appearing to simplify their adoption, particularly around federated governance and self-serve platforms. The industry will consolidate best practices and lessons learned. Edge computing and real-time inference. Processing data closer to its source at the edge of the network, e.g. in IoT devices, smart factories, will become more prevalent, driven by low-latency requirements and bandwidth constraints. Data architectures will extend to manage data pipelines that span from the edge to the cloud. Ethical AI and responsible data practices. As AI models become more pervasive, ensuring fairness, transparency, and accountability in data usage and ML models is paramount. Data architects will play a crucial role in building systems that support ethical AI development, including proper data provenance, bias detection, and explainability. Data sharing and ecosystems. Secure, efficient data sharing between organizations. Data clean rooms, data exchanges will grow, creating complex data ecosystems that demand robust architectural standards for interoperability and trust. Concluding thoughts. Data architecture is no longer just a technical discipline. It is a critical strategic capability. We've moved from merely storing data to treating it as a dynamic, living asset that fuels innovation and competitive differentiation. The role of the data architect is at the forefront of this transformation, designing, building, and nurturing the complex systems that transform raw data into invaluable insights. By embracing adaptability, focusing on foundational principles, and continuously evolving with the technological landscape, data architects will continue to shape the data-driven future. For continued learning, continually engage with industry whitepapers, attend webinars from leading cloud providers and data platform vendors, participate in open-source communities, and read seminal works like Martin Kleppmann's Designing Data-Intensive Applications or the evolving discussions around data mesh by Zhamak Dehghani and others. The journey of a data architect is a continuous pursuit of knowledge and practical mastery, always building for the future.